Boa tarde a todos, obrigado pela presença de vocês. Hoje temos a honra de ter o professor Brian para uma palestra aqui sobre manufatura avançada, robótica, essas coisas da quarta revolução industrial. Essa palestra vai ser de mais ou menos 1 hora e a gente vai ter a oportunidade também de fazer perguntas para o professor. Então fiquem à vontade para perguntar as coisas. Não é todos os dias que temos o prazer de receber o professor. Então é isso. Professor, thank you very much for your presence here today. And that's it.
Great. Well, thank you very much. Let me just get rid of one thing here. Okay, well, it's a pleasure to be here, right? The director, Pierre Matte, invited me to come. He's had me visit a lot of interesting places, CNH, right, and so forth. And so this is the 4th talk, right, that Pierre's had me give in 4 different topics, right? But hopefully I'll do this one justice, right? So what I'll talk about today is some of the work that we've been doing in kind of continuous task planning and execution, and in the context of human and human-robot collaboration, and I'll try to set it in the context of manufacturing, right? You guys know a lot about manufacturing, so rather than showing you assembly lines, I'll actually show you something very different, which is deep sea exploration, but it turns out that managing an ocean expedition and managing a factory has more commonality than you might think, right? And it'll make the topic a little bit more interesting to you, right? But then we'll have to talk about the analogy a bit. Now, in the process of this talk, Pierre had a whole bunch of different topics that he'd like me to talk about, more than you have patience for. So my purpose is not to give the whole talk, right? My purpose is just to engage in a dialogue. So I hope that you'll ask as many questions as possible, and then it doesn't really matter how far I get into the talk. I can talk as long or short as you like. Okay, so to start, what my group has been focusing on is kind of AI and robotics, but what we do is we look at the part of robotics which kind of relates to how we think. So we focus more on cognitive robotics, right? And in this case, we want to be able to have robotic systems which can plan and execute tasks kind of at the cognitive level which people do it, right? And then the second part is we would like those systems to be able to interact with people, right? And the fact that they're reasoning at a level which is similar to what humans are doing can help facilitate the effectiveness of that dialogue, right? So I just want to kind of get you some examples of that kind of reasoning, right? And then we can talk about why that's applicable in the manufacturing context. Now, the features of our systems that we are developing is, one is we don't want to tell them the details of how to do something, right? If you interact with another human, your teenage daughter, your teenage son, you don't tell them what to do, right? You can give them some goals, right? And then they're going to do what they want. So you want an autonomous system which is smart enough that you give it the goals, right? And then it's going to figure out how to do that. And then the advantage of that is in an uncertain environment, right? If you tell the system the goals, but you give it flexibility, then you can use that flexibility to adapt to this situation. It either adapts to recover for failure, or it adapts to become more efficient, right? Or to manage risk, okay? So the notion of a goal-directed system is fundamental to us. When we program a system, what does it mean to program in terms of goals as opposed to actions, right? If we communicate to a system, what does it mean to communicate those goals? If there's some disagreement, right, between the operator and what the automation can do, then how do they renegotiate its goals? So goal-directed is very important to us, right? That most of the problems that we look at involve some combination of planning tasks, but planning motions, right? Pretty much every application we look at, either you're planning motions or you're planning control trajectories. So you need the system to be able to address that problem and address it effectively. But we want it to be able to go from the level of high-level goals and planning the sequence of activities, so that's, or the activity planning, and then often the motions and the activities are very tightly coupled. So you can't view those as two different, purely independent problems. You need to be able to think about when do they need to be coordinated and when do they need to be coordinated effectively. And often that is the case that the amount of time that state couples to time, because the time that it takes a motion, right, affects the duration of activities. How much time you have affects how smooth the motion can be. If there's uncertainty in your motion, then that translates into uncertainty and certainly in the duration of activity. So risk management involves combining the both. So we're always doing some combination of planning tasks, activities, and planning motions. Efficiency is important, right? And robustness is important. So we'll address efficiency and robustness by constantly replanning online and deferring decisions as much as possible. We want our systems to be risk sensitive. So I've done a lot of work in autonomous systems for the last 30 years. We started with deep space probes. So my team developed a system, right, which could take a set of mission goals, plan its missions, diagnose, repair, reconfigure the spacecraft, right? We deployed this on an asteroid comet flyby, but the immediate issue people say when they actually start operating the system is how do you guarantee the success of the mission, right? So how do you manage risk, right? So we found that it's very important for autonomous systems, right, or any kind of automation to be able to know about uncertainty, know what's considered to be safe enough, and then have guarantees of safety and correctness, right? And then finally, in terms of interacting, right, with an operator, right, then an operator has a set of insights, right, or a user, right, and those are not captured in your model. Our systems are reasoning from a model, so their reasoning is only as good as the model, right, but they're a pale abstraction of the world. The operator has a richer understanding of that model, so you always want the operator, right, and the automation to work together and to complement each other. Usually, you need to have a dialogue when there's some disagreement between what the automation says is possible and then what the user says they want. So we want to use that disagreement as a focus of negotiation. And I'll give you some examples of that. Okay. Now, it's less true in manufacturing. In those cases where I'm talking about ocean exploration, then these are information-seeking systems, right? If we talk about agriculture and we're trying to do agriculture monitoring, then those mobile satellites, right, or observing systems, right, are seeking information. So that'll be a theme in our research, but it's less important for today's talk. So manufacturing, right? So in manufacturing, what I'll do is I'll try to speak to two different levels of manufacturing. Really, the first level of manufacturing is looking at the factory level and managing the overall factory process, right? So I'll talk about techniques which are applicable to managing the overall factory process. And we've looked at that, for example, with companies like Boeing, right, and applied our techniques there. Rather than talking about the assembly line there, that's where I'll use ocean exploration and the fact how a chief scientist and a captain manage the crew, manage those resources, and manage the deployments, right? As an example of a process that you're managing, but what's interesting there is there's a lot of uncertainty, right, and dynamic changes in the environment. So it stretches the problem. And then the second level that I'll look at is at the factory cell level, right? So how do you do coordination between the automation, or how do you do coordination between multiple robot manipulators? So I'll look both at the problem of how do you do cooperative teamwork where it's robot-robot, and then I'll also talk about human-robot. And then there is one level below that, which is how do you effectively control the individual manipulator? And there's a lot of work that we've done there, but I'll focus more at coordination, so I'll look at the cell level and the factory level. Okay? So if you look at the requirements at that level, right, then each has a set of drivers, right? So for example, at the factory level, right, you want to be able to handle, you're managing the production line activities. There is uncertainty, and the uncertainty can just either be uncertainty in terms of how long it takes an activity. That may be known very well, right? But when there's a disruption in the line, something breaks, right, then that changes the amount of time. If somebody calls in sick and you have to change your in and out your work staff, then again you have a disruption. So it's at some level a scheduling problem, right? But when you're solving that scheduling problem, you want to make sure that you put in some safety margins. You don't want to have too much of a safety margin. You don't have too little of a safety margin, but you want the systems, right, which are doing scheduling and the resource allocation to know about uncertainty, know about risk, and know how to manage them effectively. A second one is the problem of resolving failures, which could lead to oversubscription, right? The system is trying to do too much, right? And so what you end up doing is, because of failure and it's trying to do too much, right, you have to figure out how to adapt the assembly line. It couldn't just be that you're switching resources, but it could be that you're trying to do less. So how do you help an operator effectively kind of manage those reconfigurations of the system to deal with oversubscription? And how does the automation interact with the user? The last one is that usually when we have a set of workstations, right, then we can either have a conveyor belt which moves from workstation to workstation, or you can use unmanned ground vehicles, right, to move things from one workstation to another. If you have that context, then it becomes more like an autonomous car problem, right? That you have traffic that's moving around, right? You need to make sure that you don't have collisions with those vehicles. You need to make sure that it's safe for the workers who are around. So there is a mobile vehicle problem to managing the factory floor. And if I have time, I'll talk about that, but probably not. Okay. If you look at the cell level, then it's a bit different, right? So at the cell level, right, we want to be able to set up a cell and we want to program it very quickly, right? Today, in terms of factory automation, the cost increasingly is in the setup, right? Writing the procedures to control the factory cell and then writing the repair procedures. So a barrier to deployment is to be able to program, right, the factory cells quickly, and that you can view as a planning process, right? And so if we want to have a wider deployment or reconfigure a factory very quickly to different products, then we would need to automate that process of writing those programs. When we were talking about humans working with a robot, right, then a barrier to a human and a robot being in the same spot is the safety, right, of the worker. In those cases, for an arm to work around them, because a human is a moving obstacle, then what you need to do is to be able to predict where the human is likely to go, and then make sure that your motions are safe with respect to where the human is. Humans are intelligent people who have goals, right? And so if you want to be able to infer where they're going, then you can't just track their motion, right? What you need to be able to do is to understand what their intentions are, what they're doing, and use that to predict where they are, and then move safely around them. And then we also want these robotic systems to fail gracefully, right? So as these are operating for a significant period of time, then if they fail, then they can disrupt the factory. So rather than dealing with that disruption after the fact, you'd like to be able to predict that they're on the onset of failure. You like the systems to basically gracefully degrade, right? If it's a mobile vehicle, then you like to move to a place where it can be easily repaired. You like it to work in a degraded mode. So failure is a very important issue, right? And techniques for kind of inferring the onset of failure are very important. Again, we've done a lot of research in there. Whether or not there's time for that, we'll have to see. Okay. Now, as I said, we're going to use some work in ocean exploration as an analogy. I think it's kind of a fun topic to talk about near the end of the week, and then a lot of the technologies we developed for the factory we've been now applying for deep sea exploration. So I thought I'd use those examples by analogy. The analogy here is that when you manage a ship, so we were on this ship in January for a month, right? My students, myself. We had 18 scientists and a crew of 20-some people. So we have about 40 people altogether on the ship, right? We're managing a whole series of missions involving about 6 to 8 autonomous underwater vehicles, right? But the ship and the crew have responsibility of deploying the science instruments, the underwater vehicles, bringing them back. They have 2 boats here plus 2 cranes that they're using to do those operations. So it's a fairly complicated process, right? The ship is the centerpiece of it because it's trying to do all these tasks at once, but it's having to deal with a lot of disruption and uncertainty. And the reason why is that the ship is, you can think of it as being like a sheepdog, right? Where the vehicles are a bunch of sheep and they kind of wander off because of the currents push them around. So the ship needs to stay close. So it's constantly replanning, right, its activities, right, when one underwater vehicle drifts too far away or another, right? So it's a very interesting test bed for a dynamic process. But a lot of the coordination is coordinating with the crew as much as the coordination of the vehicles. So I'll look at the robot coordination and the human coordination in that context. The cell level then ends up being more of how do we coordinate a set of vehicles, right, to do a mission, right, where we're having to deal more with how do we avoid them from colliding, but how do they behave effectively together. So I'll talk a little bit about that, but then I'll shift to human-robot collaboration in a manufacturing context, and we'll look at wing assembly, right, at Boeing. Okay, so that's the game plan, right? It's understand techniques at the factory level, the cell level. The way that I'll do that is through the following 3 to 4 topics. First, I'll just talk about what does it mean for a goal-directed system, and what does it mean to ask a goal-directed system to do a set of tasks. Concretely, what does it look like, right? And I'll do that both if you were programming this system, which I'll do lightly, and then also if you were just talking to the robot directly, okay? Beginning with the speech dialogue systems that are publicly available. I'll then look at the underwater scenarios, right, to kind of talk about more the factory floor level, and I'll emphasize 3 topics there. The first topic will be how do we have systems that know about risk when they're planning, right, and are risk sensitive, and how do they adapt to risk. The second is how do we help the human teams do the coordination, and then third, how will we help the robots, which move around, to do coordination. From there, I'll then shift to human-robot collaboration, and that'll be in the industrial context, right? And I'll show you a bunch of different types of ideas which help a human and a robot kind of adapt to each other, right? And that's kind of the main focus of the talk. If there is time, then I could also talk about tight coordination under risk with vehicles, right? Or as I said, in the factory floor, those vehicles are interacting together. In this case, I'll talk about them in the context of autonomous cars and in challenging traffic situations. But the ideas carry over. And in that case, we're focusing on the issue of autonomous systems not only should plan and assess for risk when other agents are around, not only should they predict what they're doing, but they also should always be planning contingencies and backups. Okay, so let me just start with the first objective, which is talking about goal-directed systems. Let me first talk about how to program them. So if you look at programming of a robotic system, and most robotic systems are the same. Either you program them by showing them what to do, you move the manipulator around, and then you just do motion capture, right? And then it does a rote playback of that, right? Or what you end up doing is you write a very simple program, which is a sequence of actions, such as a sequence of waypoints, and then the robot just follows those waypoints. When I first worked with NASA, that's how our deep space probes are controlled, right? You look at a Mars rover, then that's how a Mars rover is programmed, right? You look at an orbiting spacecraft, right? So they're programmed at a level at a lower level of programming than, well, we used to program our VCR, right? So a very simple level, right? Most factory automation's like that. And that doesn't provide much flexibility for the system to adapt to the environment, and it's very time consuming. So in the factory context, right, that is a big barrier, right, in terms of programming the system. What we ideally want to be able to do is to talk to the system like you would talk to the human who is operating the vehicle, right? So if I was talking to somebody who was piloting this vehicle, right, and I had it putting out a fire, then what I would say to the operator is, look, I'd like you to put these 2 fires out, and then I'd like you to be back in an hour. Here, let me show you a map, right, and you figure it out, right? We don't want to be programming at this level. Okay, so what would it be like to program a system at that level? So I'll give you a simple example of a snippet of a piece of code. So we developed a language called RMPL. This version of it looks like Java in terms of its syntax, right? But you program at the Go level, and I'll explain what that means. So here's the English that I said over here. Put out the fires at 2 locations and return to the base in an hour. In a Java-like language, I could write this program, and the program simply says, I want the first fire out, I then want the second fire out, and then I wanted my UAV to back at base, and I want it to be landed, okay? And I want to do that in an hour, right? So it's pretty much a direct translation. It also looks like a Java program, right? There's only one difference that I've done, right? Which is I have some state variables called fire, right, in the UAV, and I can assign their values. Now, what's a little bit weird about that is I've assumed that I can just act like a god and put the fire out in the external world, and the fire is out. So the program is simple. What's hard to do is to execute the program, right? So let's look at so when I execute the program, the system has to figure out how do I achieve the state of having the fire out. And that's the planning problem that the execution system or the execution kernel language will have to address. But the programming metaphor is fairly simple, right? Which is in our program, we'll specify what the states of the world are and how do I change that state. Given that, then when I write a program, I can just assign the state of the world, and I can pretend that every state in the world can be touched, Okay, so that's the programming metaphor. Otherwise, you use a traditional programming constructs. So now if I want to execute this program, right, then I need to give a map. So here's a map. So here's a map which shows where the UAV is, right? It shows where the 2 fires are, and it shows some other relevant resources. So we have some lakes here. There can be places to refuel. In this case, there is a mountain. There's some wind power, and those are places that I want to avoid. So I contain that in my map. So the interpreter of my language, I give it a map of the world. I give it the vehicle dynamics as well. And then I want to tell the system what kinds of commands that I'll provide. So any vendor, right, for a robotic system, an assembly line, air vehicle, usually gives you a manual with a set of primitive commands that you can send to it. So here's those primitive commands here. So our vehicle can take off, it can land, right? It can move between 2 locations. It can pick up water, right? And then it can drop water, right? And in our simple model here, we have 2 steps of dropping water off before the fire is completely out. So we tell the system, right, these are the commands it can do. We also tell it a little bit more information. We tell it when it can do it. So to take off, we need to be on the ground, not flying. And after we take off, we'll be flying. This says that in order to drop water from a high elevation, I need to be flying, I need to have water loaded, I need to be over the fire, and the fire level will be high. As a result, I don't have any water, and the fire will be medium. Okay, so we've told the system that information. It's not hard to provide that, right? We only do that once, and then we just write this program. So what is it like to execute this program? So here's an example. I can find my mouse. There we go. Okay, so the language RMPL has an executive called Enterprise. This is Enterprise's execution of that program. Okay, and this is what we have students using, right, in the lab. Okay, so what you'll notice, right, is to put out the first fire, right, it took off, it flew, picked up water, right, it went to the fire, it dropped it off, it goes, gets some more water, goes back here, drops it off, and then it works on the next fire, and then it gets back. Okay, so in doing this, it had to plan a sequence of actions, and it came up with that plan by looking at the primitives, right? And now activity planning algorithms have gone fast enough that it can do that quite quickly. And then it needed to do the motion planning, right? So it needed to fly the vehicle while using the vehicle dynamics, right? It needed to avoid the obstacles. The planner here and the motion and the activity planner and the motion planner in this demo are simpler versions of those, but we've used more complicated versions, and you'll see those in the underwater examples. So what I just want you to get here is the idea that you can interact with these systems by taking the traditional programming, the notions of programming, but you can abstract that by simply talking about programming in terms of state, describing how to change the state of the world, and then when you execute these programs or compile them down into some traditional language, we're using planning algorithms, right, to be able to generate the execution. And then you can layer complexity on it. So you can add in timing constraints, you can add in constraints on risk, right? You can make it multi-vehicle, right? You can incorporate more of the dynamics of the system, but the same idea carries over. The other thing is we wanted to make this easy to use, right? So in this case, right, the example we gave here is we did an experiment where we took a bunch of MIT freshmen. They're smart, right? But they're freshmen, first year, right? We took those who had never programmed before, and we had a 3-week course for them where we gave them challenges, and then we give them the system. We'd say, you can program in this way, and then we'd have them try the challenge, and then we would make the system a little bit smarter, and we give them the challenge again. What we found is that students were able to use this quite easily without understanding a lot of the algorithms and the technology. Now, an academic test is only so useful, so you really want to take this out into the field. So before taking this out into the field, well, just before I talk about that, so what is it like under the hood, right? So the students wouldn't see this, right? Or the user wouldn't see this, right? But if you actually look at what the system is doing, right, then it plans a set of activities. So there's a range of different kinds of activity planners that we've used, we've developed, and that we draw from the AI planning research community, right? It needs to execute those things, and in order to execute it dynamically schedules and monitors the conditions of the world. So we have capabilities which are good at doing execution and execution monitoring, and we'll see that in the context of human-robot collaboration. We need to do path planning, right? So we have a series of algorithms, right, which do the motion planning, but those motion planners are goal-directed, and they know about timing and desired states and safety constraints. We have capabilities which are constantly estimating the state of the environment or doing diagnosis, right? And then we also, in the next series of examples, will interact with the user as well. So there's a series of capabilities. They all have a model of the world. They all share what their goals are. They all share what their state is. And then the architecture does that coordination for you. And then you just use different activity planners and motion planners depending on the property of your problem. So here's an example in the course, right? So what we would do is kind of within a day, we would have them start programming in RMPO. As soon as they got it working in simulation, then we would take them into the lab. We would just tell the environment to switch from simulation mode to the hardware mode, and then you'd start flying the vehicles, right? And so it carries over fairly simply. But that's not kind of a rendition to the real world. So the next step, right, we did was to take it out into the ocean, right? And so when we took it out into the ocean, we went to Scott's Reef, which is in the East Timor Sea, which is between Australia, right, and Indonesia, right? And then we applied the same capabilities, right, by controlling this glider, right? But this is an underwater glider, right? And so we were doing exploration of the reef with an underwater glider. Now, in those cases, right, we have to deal with timing, we have to deal with dynamics, we have to deal with currents, and we have to deal with a lot of uncertainty. So the version of the capability that we developed there, and I'll talk about in a minute, knows about uncertainty and risk and guarantees the safety of the vehicle with respect to certain constraints by the operator. Okay, so that's what it would be like if we programmed this system. But there's a number of people who don't really want to program these systems, right? You'd like to have a natural interface. So let me give you an example of that. But I kind of try to show you a little bit about what's under the hood. So this is a project, right, that Boeing asked us to do. So they said, suppose we have a personal air vehicle. Right, so they had been studying the concept of a dual mode vehicle, right, which could fly, right, it could drive, and you can move back and forth. And the idea was that if you want to have wide adoption, then people can't be pilots. So what we'll do is we'll provide the notion of a robotic air taxi, and the robotic air taxi will control the system. So they gave us the hardware and then said, how do you develop a system which can do the kind of reasoning I showed you before, which can control that kind of vehicle. So it was an interesting exploration. So in order to do this, what you want is a system which can pilot, right? So it can safely pilot, right? That it can think about alternative landing sites along the way, always plan contingencies, right? And kind of adapt, right? And Claudio's group and my group has explored that a lot, right? That it knows about risks, right? So it can know about the risk of collision. It can know about the risk of going into a weather system, which will make the passenger sick. And it can also know about the risk of getting to its destination too late. And the system is effective at managing all of those risks, right? And then finally, if the user asks the system to do something and it becomes too risky, then you want the system to be helpful. So you want it to be able to say, look, it's too risky to make sure the passenger is safe, but you want the system to make recommendations. So the kinds of recommendations you may make would be things like for the car, you'd say, take me to the airport and take me to dinner along the way, but you're starting to run late. So the advice would be, go to the airport first and then eat at the airport, right? So you can kind of manage the risk. So our system kind of knows about those. They know about human preferences and adapt. So I just would want you to see the idea of how a system can collaborate with an operator, right, to deal with failure. So let me just give you then a demo of the system, and then we can talk a little bit about the technology under the hood. Can I get the sound for that?
Any more preferences?
I want to be there in 3 minutes.
Anything else?
I want to stop at Leisureland.
Any other requirement?
No.
We cannot get there in 3 minutes, but we can get there in 6 minutes.
That's fine.
Okay. I have a valid plan. There is a change in the weather condition. I will replan the path. The current destination is unavailable. Diverting to the preferred alternate landing site, Harvey Field.
Okay, so I think that's enough to get the concepts. So if you look at what's going on here, right, it's a simple user interaction, hopefully. It could be made better, right? The demo is about maybe 7 years, so 8 or 9 years by now, right? But there's a couple things that it was doing kind of under the hood. So the first is that it's maintaining a collaborative dialogue, right? So the user is given a set of goals, right, objectives, right? The system finds out that it can't do that. And when it does that, it tried to plan the set of activities, it tried to plan the motions, which is its activity and motion planner, Kirk and Sulu, and together they found out the problem wasn't solvable. So they couldn't just go back and say, I can't do it, right? What they need to do is to figure out why it failed, right? The system could explain to the user, we didn't have in this demo, but it could explain to the user why it isn't possible, and then the system makes recommendations, right, to how to adapt things. So there's that collaborative dialogue, and we view that collaborative dialogue as a diagnostic process, right? We're not diagnosing hardware. In this case, we're diagnosing the user requirements of why the goals can't be met, okay? And we apply a lot of hardware diagnosis algorithms, right, to do that diagnosis. The second is that it manages risk-taking, right? So the system was reasoning about the risk at the activity planning level in terms of arriving too late, and the risk at the motion planning level. When you're trying to manage that risk, you have to decide how much risk that you're willing to accept with respect to motions and collisions and not meeting your deadline. So the ability to do that coordination and risk is very important. Right? The system knows what the top level goals are. It knows how the different actions and different motions support those goals, and then it's always monitoring the progress of those goals and sub-goals. So if something changes in the environment and it's irrelevant to the plan, then the system ignores it. But if it observes things in the environment which will cause it to fail downstream, then it immediately detects that and plans. So the ability to be able to detect that you're eventually going to fail, as opposed to waiting till you fail, gives the system a lot more latitude to adapt and allows you to reduce disruption. And then finally, there's the notion that the system is able to construct a backup plan. In this case, the backup plan was having alternative landing sites. And work that we've been doing more and more, we're constantly having the system come up with backup plans. So the idea isn't to replan when there's a failure. The idea is when failure is looking more possible but not likely yet, the system should always be coming up with a backup plan for each of those options, right? So you can always switch to them as appropriate. Okay, so that's the kinds of behaviors that you were getting. How did we get it? So I'm just going to focus on the one part of that, which is the generation of the collaborative dialogue, right, to give you a little bit of a sense of the technical ideas, right? So our system, right, that we are interacting with in the personal transportation system has a natural language interface, right? And that may be something that we didn't know so much about 3 or 4 years ago, but everybody knows it now, right? If you look at the Amazon Echo, Siri, Cortana, all those systems, right? So what those systems have, right, is they have a speech recognition system. Deep nets have made the speech much more reliable, right? It has a natural language parsing system, right? So you can get a parse tree from the English sentences, right? And then usually they have a knowledge base behind them. And most of those systems, right, are a combination of those three things. They don't know anything about tasks. They don't know anything about goals, right? They don't know anything about monitoring. So they're not experts in terms of task planning and execution, the kinds of stuff that you guys do in manufacturing, right? So our system is very capable in terms of planning tasks and motions, right? And diagnosing failures in those. And so that's what's going on in our system. So what happened is that, and our three components are, Kirk is doing the task planning, Sue is doing the motion planning, and Uhura is dealing with diagnosing the goal and goal failure. So let's see how the three work together to produce that fragment of a dialogue at the beginning of the movie. So Uhura is communicating to the user through the dialogue management system. And so the user said, I want to go to Boeing in 35 minutes. Uhura says, what does that mean? What it means is I want to go from home to Boeing. So there's an activity, and I want it to take at most 35 minutes. So it writes that down. Looks like a plan, but it's an abstract plan. Okay. Then the user says, I want to stop at Tacoma Airport for 20 to 30 minutes. So there's an activity to be there and then to go and depart, right? And then that's the end of its goals. Okay. So Uhura has constructed this goal description and asked Kirk and Sulu to generate an executable plan. Okay. So Kirk and Sulu are asked to do that, and they try to do that, right? So Kirk fleshes out the activity and asks Sulu to move between the airports. What they collectively learn is that it's going to take 10 to 15 minutes to go to Tacoma, and then 10 to 15 minutes to get to Boeing, right? And then if we look at that, then that's not feasible, right? So if you look at where it's infeasible, right, then it would take at least 30 minutes before you can leave Tacoma, right? But the user said you have to leave within 25 minutes, and that's just not possible, right? So we have a conflict between those two constraints and that constraint there, okay? So the system has identified that failure. It could explain to the user that failure, but it needs to resolve it, right? So the way that it resolves it is it says, first it says, I have a problem, right? Could explain why it has a problem, and then it can make some suggestions. So one change to do would be to relax this constraint. So rather than dropping some of the user goals, we try to weaken the user goals. So we say, how about if I leave in 15 minutes as opposed to 20 minutes? Right? And then that would be consistent. 10 plus 15 is 25. That meets the upper bound of 25, and it's happy, right? But the user doesn't like that, okay? So the user says, no, I don't want to do that. So the system continues on. So it can't change this time. It can't change physics, but it could change this. So it'll recommend, right, to spend an additional 5 minutes, right, before leaving Tacoma. So it considers that, but before recommending that back to the user, it has to say, will that work, or are there other problems? So it then looks at this constraint up here. So if this is 30 minutes, right, and we then add 10 minutes here, then it'll take at least 40 minutes until we arrive at Boeing, but we have at most 35 minutes. So we have another conflict here. We need to resolve that conflict, right? And there's a number of ways that we can do that, right? But one way to resolve that is to extend this 35 to 5 minutes, okay? So that's in the dialogue where you heard the system say, can you delay your takeoff slot at Tacoma by 5 minutes and your arrival by 5 minutes? And then the user said yes, okay? So what the algorithm is doing is it's considering what the minimal relaxations to the user goals are and then proposing minimal relaxations. Now you then have to decide which ones are better or not. So what it's doing is it's using a model, the user preference, to decide which of these kinds of changes are more preferable, right? You have to figure out where that preference model comes from, so we learn that automatically, right? For example, from the web, right? So there's a learning problem to analyze the data to learn that preference. Okay. So that just kind of gives you a sense of the kind of reasoning that you involve to kind of support that kind of interaction. Okay. So the next thing that I want to do is to then show how we're using some of these ideas out in the field in the ocean context. Okay. So as I said, I'll look at 3 different ocean campaigns that we've done during the last 3 years, right, roughly, or one a few years ago, which was in Scott's Reef, which I showed you there. In January, we spent a month in Hawaii at the Ao Channel between Maui and Lanai, and then next December we'll be in Costa Rica, where we're doing more manipulation, sample return, and then we're going to be going to the Colombo volcano in about a year from now. Okay, so here's the first example I gave you, right? So we had the Falkor ship. We're going to Scott's Reef. We have this set of vehicles that we're trying to control, and historically you have one ship controlling one vehicle. It was novel to be able to try that many underwater vehicles off of one ship, and every one of these vehicles is different, right? This is our glider. It has no propeller. It just glides up and down, right? These are propelled vehicles. This one can go off for about a month, right? These can go off for about 8 hours. This vehicle is very maneuverable, has a high resolution camera. It can go off for 8 hours or less. This has a high resolution camera, but it just floats and kind of goes up and down, very uncontrollable. This is called a wave glider. It goes on the surface, right? And it has a solar array, and it's gone all the way from California to Hawaii and back again. It can kind of go on pretty much forever. What's interesting in this case is you have a lot of vehicles operating in the same space, but they have very different modalities and time scales. Every one is different. So if you develop a different approach of programming each one, right, then it's going to take a long time to be able to control them and coordinate them. So our ability to provide a technology which easily adapts to different vehicle types, right, is very important. Our focus then was not controlling all these vehicles, right? It was controlling the glider, which is a very under-actuated robotic system. So it really gets pushed to deal with uncertainty, or pushed by the uncertainty of the waves and the currents. It was designed to operate in the middle of the ocean, but we're operating it in a reef which is very turbulent. So the idea is have it operate in very risky situations, and then it becomes a much more interesting system. So here's just a point which emphasizes risk. So we probably had about a half a dozen encounters over the 3 weeks where different vehicles had near misses. Let me just give you one of them. Oops. See where my mouse is. Here we go. So this is called the photo float, right? The photo float just moves up and down. And I'm almost collided within the Iver. The photo float was quite popular in collisions, so we have another one where it was almost chopped up by the Falcar propeller. It just kind of started scooting away just as it started getting chopped up. The wave glider, right? We were in the galley, we were looking out a porthole, and we just suddenly saw the wave glider come within a meter of the ship, right? So lots of these encounters, right? So it just becomes too complicated for the operator to deal with this level of complexity. We're trying to help the operator manage that complexity by having situational awareness, right? Deal with risk and then adapt very quickly. So before I had talked about commanding the system, right? At this level, and I showed you 2 examples of commanding at this level. What I showed you so far doesn't know about uncertainty and risk, right? So when I use those words, I mean 2 things, right? When I talk about uncertainty, what I talk about is the probabilistic uncertainty of how long it will take, right? The uncertainty of motion, your sensor uncertainty. So that's one thing you want to do. Risk, by risk, what I'm talking about is what we consider to be the acceptable risk. So how safe do you want the system to be? Now we could say we want it to be safe, right? But in an uncertain world where uncertainty is unbounded, for example, Gaussians are unbounded, then you can't guarantee safety. There's always some probability of failure. Right? The engineer may pretend that it's safe by putting in a safety margin, but they're doing the approximation. Really what you want to do is you want to have a requirement in terms of safety, which is, for example, the probability of collision, right, is 1%, or the probability of a car accident, right, is 0.01%, right? But usually we do have those kinds of constraints, and then we want to make sure that the system operates within those constraints. So in this mission, we may want to talk about the risk of not putting out the fire and the risk of losing our vehicle. So the operator also specifies the acceptable risk. So we may say that the probability of not putting out the fire and then having to go back is 5%, but the probability of losing our vehicle due to collision should be 0.1%. So in our paradigm, you write the program or you give the description and then you specify the acceptable risk for different segments. And it's usually 2 things. One is safety and then the other one is success of different mission activities. Okay? Given that, then the system operates to be able to guarantee those risk bounds. So how do we have a system which guarantees risk bounds? So Claudio and I both worked on this. I'll give you a very simple example just to give you the idea. So in this case, suppose we're going from this location to this location. We know the vehicle dynamics. We know the equations of those. There may be some uncertainty in parameter estimates. We write those down. We have some sensor uncertainty. We have some actuation uncertainty. So we put those in our model. So it becomes a stochastic model. And then we specify what we consider to be the acceptable risk. So we might specify, for example, that the probability of some failure is less than some quantity delta. We'll refer to that as a chance constraint. Okay? So given this chance constraint, the problem ends up being to find a path in which the probability of failure along the path accumulates to most delta. So that's the problem that we need to solve. And then the optimization problem is to find the best path, right? Either the most energy efficient, the fastest, the one that gives us the most information while respecting the chance constraint. So that's a stochastic optimization problem, right? There are techniques to do that, but they tend not to scale very well. We want to solve very large problems. So a lot of our research is focused on algorithms which can do this planning very efficiently, okay? And then that becomes an enabler. But I want you to have the idea of a risk-bounded approach, and it's really rooted in the notion of writing down chance constraints and then acquiring models of the uncertainty. Okay, so I'll just give you a little bit about the intuition, right? Because it's a kind of a broad talk about how we'll solve this algorithmically, right? So here's a similar problem, right? So here we'll take a race car, it goes from the start, it crosses the finish line. The probability of failing is 0.1%. So that's our delta, right? So that's our risk bound. So if I was going to solve this problem, or I was going to have my teenage daughter or son solve this problem, then we as humans don't like to reason about uncertainty. So what we do is we put in a safety margin. And once we have the safety margin, then we solve the deterministic problem. We assume that the safety margin has encapsulated what we wanted about the uncertainty. we have a lot more deterministic optimization algorithms than stochastic optimization problems. So if we can build in a safety margin for our deterministic algorithms, then we can use all the off-the-shelf deterministic solvers. So that's what we'll do here. So here's a safety margin, right? So we create a safety margin that satisfies the risk bound. So the probability, right, of crossing the safety margin is at most delta, right? And then once we put in the safety margin, then we reframe the problem, right, where we take the nominal trajectory, we drop the noise, and we find a trajectory which works within the safety margin. Okay, so that makes it a much easier problem to solve. The thing is that the safety margin, if we don't design it correctly, may not be very efficient, right? So we can come up with a better safety margin here, right? So that's one safety margin. As a skill driver, right, what we would do is we would take a safety margin where the area is the same, so the risk is the same, right, but which gets us across the finish line a lot faster, right? So what was important in coming up with this path, and this is what we normally do, is when we're in the straightaway of the road, there's really no value getting close to the edge, so we just stay in the middle because that's the safest, right? Okay? The benefit that we get is on the corner. So what we do is we decide to spend the risk at the corner because we get the greatest benefit at the corner, right? We don't spend risk where we don't get that much benefit. Okay? So what's important here is that when you say I want a probability of success of 99.9, you told me that I can fail 0.01, right? So you give me some license to fail, right? So that's a resource, so it's precious, right? But we are given that resource, and we'll try to use that to effect. So in this case, I'll use it, right, to get the highest utility, which is to cross the finish line as fast as possible. Okay, I might use it to be able to do less reasoning about unlikely options, which we'd see later. Okay. So let me just kind of give you a very simple algorithm to doing this. We've developed a whole suite of these, but this is the most intuitive and most general. So what this algorithm called iterative risk allocation does is it decides how to spend the risk. How it spends the risk implies a safety margin. We write down that safety margin. We determinize our problem. We solve that problem for that safety margin. And then we analyze our use of risk and say, how good was it? And then we try to reallocate the risk to come up with a better safety margin and a better solution. So we just are iterating the allocation of the risk and the deterministic problem. So here we start with a uniform distribution safety margin, which is easiest. So we take the same risk at every step in the plan. We generate a solution, and then we analyze it. So here what we notice is that the path hit the safety margin here, and it didn't hit it here. So mathematically, the constraints are active here, and they're inactive here, okay? So where they're inactive, right, then I didn't use the risk that I spent. So what I'll do is I'll spend less risk. If I want to take less risk, I need to have a bigger safety margin. So I'm going to grow the safety margins here, okay? So that's what I do. Now, if I compute the risk that I'm taking, then it's less than delta, right? So I take the excess risk, and I reallocate it to the active constraint here. And by taking more risk, I can make the safety margin smaller, and I can move closer. So that's what the algorithm does here, okay? So it has a new safety margin, and then we compute the next best path. That's what it does, and then we just keep doing that, okay? So in this case, this algorithm, right, is guaranteed to improve at every step. It's not guaranteed to come up with the optimal solution. In practice, it works pretty effectively. And it didn't care about the form of the optimization problem, so you can use this approach for a wide family of planning problems. Right? We've also worked on a large number of algorithms which guarantee convergence, right, for different problems, for linear programs, for complex programs, right, and the likes, but those algorithms are more complicated. Okay, so we took that idea, right, and then we applied those ideas and generalized them to Kirk and Sulu. So Sulu, right, the motion planner, basically was using this kind of algorithm. Kirk, the activity planner, needs to know about deadlines and scheduling. So we have a risk-bounded scheduler, which is using similar kinds of ideas. Okay? And then they work together. So to control the underwater glider, right, then this is the underwater glider, right? For those who are interested, right, the way that the glider works, because it has no propeller, is it tips its nose down, right? It then reduces its buoyancy, and then the wings push it forward. It then gets to the bottom, right? It tips its nose up, increases its buoyancy, and moves up. So it only uses energy, right, when it flips, right? So if it can go very deep, right, then it doesn't use very much energy. If it's shallow, right, then it has to yo-yo up and down a lot, right? So that's our planning problem. But you can also see in that case that vehicle, that current, it goes kind of at the same speed as currents, and so the currents can really push it along. So there's a lot of uncertainty and risk in it. So we need to be able to plan the paths, right, for the glider, right? But we also need to plan the activity. So the way that the operator interacts with it is it says, here are some different places, right, that I want you to go to. I want you to kind of do a transect between 2 points in these areas. You can visit them in any order that you want to. We then tell it where the other circus of vehicles are. At that time, we tell it current models, the uncertainty of these places, and then it needs to find out what the subset of the science goals are and the order of them to do it efficiently. So you can think of this as a motor vehicle routing with time window problem to couple together a motion planning, but this is a risk-bounded version. In manufacturing, you see similar kinds of job shop scheduling problems, but in this case, we're adding the uncertainty to it. Okay, and then here's just some rules of the road. So we would give the system these rules of the road, right? It would do combined activity and motion planning. And so for a 1 week period, right, we then operated the glider, right, in Scott's Reef. And then we went back, right, a year later, and we went to Santa Barbara, and then for the whole 3 week period, the operator no longer hand-coded the system anymore. The stuff was robust enough that they just used this approach. The net effect is that when people hand code the operations of these systems, the scripts tend to fail, right, about 50% of the time, and we were getting almost 100% success, and we were able to do missions that they weren't able to do. Now, in this case, right, I talked about uncertainty in terms of the motions, but in fact, uncertainty is everywhere, right? There's uncertainty in how long it takes to do an activity, right? There's uncertainty in the state, which is what we just addressed, right? There's uncertainty in the resources, how much charge you have left, right? And there's model uncertainty. So the planning algorithms ultimately have to deal with all those kinds of uncertainty. They need to manage the risk amongst all those. And so if I gave you a longer talk, we would talk about how to address each of those. Okay, and so the architecture I showed you earlier, there's probabilistic versions of each of those. So it deals with the uncertainty and the activity planning, the motion planning, and how uncertainty in motion translates into uncertainty in time. When we have a dialogue, like I showed you earlier, then the system is also thinking about risk. So it may not say, I can't reach your destination. It would say, it's starting to get risky. Are you willing to accept more risk, or would you like to reduce the risk by adjusting things? So it does those kinds of things. When the state isn't directly observable, then we need to estimate the state of it. So we have systems that are estimating the state of it. And when we have failure, then it's estimating the failure mode as well as the continuous state. So we just enrich the architecture. Okay, so that's about the issue of risk. Let me talk about human-robot collaboration. So this was January. So in January, we went back after several years. Same ship, the Falcor, roughly the same vehicles, right? But we were in the Lanai Channel, right? Which has a lot more current, a lot more obstacles. The obstacles are interesting. They're whales, right? And tourist boats, right, who are looking at the whales, right? So that turned out to be a real problem. You look over the side of the ship, and about 3 meters away were several whales breaching, and that was fairly commonplace. Right? So our vision in this case is we're not just going to control one glider amongst chaos, right? Now what we want to do is to have motor vehicle coordination. That's one. 2, we want to be able to do adaptive science. We want to analyze the science data and then replan based on the science data. We want to coordinate multiple vehicles, and we want to be able to coordinate the team, right? I'll just touch on those briefly. So we want robots to collaborate effectively. We want humans to collaborate effectively, right? Human collaboration ends up being to get the crew to work together, right? So that's more of a scheduling, a resource allocation. We want the teams to adapt to science opportunities very quickly. So we're closing the loop between data analytics, right, and planning, right? And then we want the teams to adapt to risk effectively, which is what I spent a lot of time talking about. So we take the same architecture we have before, right, but we add in the ability to analyze data, right, and then plan paths, right, to gather information. So that's the adaptive science. We have the user interaction, the mission planning, but in those cases, we'll use the user interaction, the mission planning to do management of the crew, which is more like managing the assembly line at one level while dealing with disturbances. And then for the path planning, we'll do path planning for multiple vehicles as opposed to one vehicle. So we're maintaining the flotilla, right, by planning for the ship and the other underwater vehicles together. Okay, so this is just about the adaptive science. I won't spend that much time to it, but to say that we have a model of the bathymetry, right, the seafloor, and we use that map to make sure that we're safe, right? We have maps of the coral reef, which is a scientific phenomenon, and our information goal is to go to different places to identify what different coral types are there. So we have a notion of interestingness and diversity, and we need to fold that into the optimization algorithm, right? So we have an optimization algorithm which tries to find a path which is safe, right, but gives us good science information. And then we have an environmental model, which is the ocean currents, and then we use that as our model of uncertainty. And then we generate a plan, we collect data, and then we replan. So we're constantly replanning. Right? In the case of a diagnostic system, if there's problems with the factory, then the kinds of adaptive collection you do is you may do some monitoring and diagnosis, and then you control the system to reveal the failure states. Okay, so let's talk about coordinating not a single vehicle or multiple vehicles, but let's do coordination on the bridge, right? So here's our chief scientist. He's responsible for coordinating the scientists, right? But mainly, scientists have different missions they want to do. The chief scientist is trying to support all of them together. The captain and crew is kind of dealing with the deployment and picking things up. And the chief scientist is an interface with the crew through the bridge officer. So they're together are responsible for coordinating the overall activity. So the chief scientist interacts with the scientists, right? The bridge officer does the crew preparation, the deployment, the retrieval, right? What makes this challenging, right, is that we have a lot of missions that we're operating at once, and they're normally used to operating one vehicle at a time at $50,000 a day. Now we have 8 different instruments operating and a half a dozen science teams, so we need to coordinate them, right? So different missions are coupled by the ship, right, physically in terms of the crew, right? Execution uncertainty is very high because of the currents, right? And because of hardware failure of these vehicles, they're very finicky, right? When a failure occurs, then you need to adapt very quickly. One of the examples in this mission is we sent our glider to go up. We were going to get our glider, and then we noticed a tourist boat who thought it was interesting, and we saw a couple guys who were drinking beer kind of go over the edge of their boat, start to pick up our glider, so we prioritized to go do that retrieval first before other things, right? There's another case where one of the vehicles called Sirius, right, was coming towards the ship while we had an ROV. We were supposed to have it stop and pick it up, but it kept on going, and it was going to a sea channel, right? So we needed to get to the sea channel, right, where it would have a collision and pick up that vehicle, but we had an ROV, a remotely operated vehicle, that we were dragging behind. So the ship tried to chase after, right, Sentry to pick it up. It couldn't go fast enough. It was getting closer and closer, so the captain had to decide to stop, take the ROV out of the water, and then chase after Sentry. So those are very risky, very uncertain situations, and the captains really want to be able to have systems which can help them make that decision-making quickly and avoid those situations before they occur, but then adapting when they have. You have the same thing in factory automation, maybe not as dramatic, right? But you want to add in enough safety margin, and then you want the system to adapt quickly and help the operator in that. So I'll just remind you of that analogy at that point. Okay, now in this case, right, for Uhura really is solving a problem of deciding a set of activities, deciding the timing, and deciding what resource to allocate it, so what crew members to allocate. So it's really a job shop scheduling problem, the same kind of problems that you have in manufacturing. The thing that we have in this case, right, is that we have uncertainty in how long it takes to do different activities. So when we represent the timing constraints for the scheduling problem, we view this as a scheduling problem with uncertainty. It's a risk-bounded problem, right? So we need to be able to come up with kind of optimal schedules with respect to a set of risk bounds in a principled manner. So that's one thing we've worked on in our algorithms. And then our system that's interacting with the operator needs to be able to know about that risk and talk about how to adjust that. Okay, so those are really, I think, the two things that are quite applicable in the manufacturing context is that user interaction and that risk-based analysis. So the one example I'll give you here then is kind of to show more the richness of that kind of negotiation. So let me just go back to the personal air vehicle example. My mouse will reappear. And then you can see what kinds of options the system could recommend. So we have some sound.
Our restaurants before going home. How much time do you have for this trip?
Complete the trip in 9 minutes.
I cannot complete the trip on time. Here is an alternative. Go to Pike Place Market for dinner and relax the trip duration from 9 minutes to 11 minutes. Is that okay?
No.
I can take you to a 2-star restaurant rather than a 4-star restaurant and only relax the duration from 9 minutes to 10 minutes. Is that okay?
No.
I can take you to Burger King rather than 2-star restaurant and complete the trip on time. Is that okay?
That's fine.
Okay, shall we start?
Yes.
Okay. Sit back, relax, and enjoy this trip.
Okay, good. So the point in this case is when a problem is oversubscribed, it's not feasible that you can do it, then there's really a rich space of things that you can do. The simplest thing that you can do is you can drop goals, right? And a lot of research was done in terms of saying what goals or what constraints you can relax. But that's really not that palatable, right? If you were saying, I want to go refuel my car and get to the airport, and you say you can't do that, then you wouldn't want to say, okay, well, either don't refuel or don't go to the airport, right? That's a ridiculous thing to do. But what you may say is, I'll go to a gas station that's closer by, but that's more expensive, right? Or that's probably the best option, right? Or so forth, right? So you want to be able to weaken your constraints as opposed to just drop the constraints. So that's the first idea, this notion of a weakening or a continuous relaxation. But then when you talk about what you can adjust, then there's a whole variety. So in our case, the problems end up being is you could adjust the timing, right? So you can weaken the timing, and you saw that, right? There's different ways to fulfill your objectives, right? So if you want to go to a restaurant, right, then your preference is to go to your favorite, right, restaurant, Japanese or whatever, right? But you can, different people have different preferences, so you can weaken those. So you could go to a Korean restaurant or so forth, right? So there is the notion of changing the way that you're fulfilling something. In the crew, you may have some crew member who's really skilled at doing this kind of support of the science mission. There may be one who's less skilled, but they're more available, so you could do that change. So you're kind of changing who's fulfilling that role, right? In machining, right, or in manufacturing, right, you could have a different tool that you use, which is less accurate, right? Or you could use a different process to do it. So you want to do those kinds of adaptations, and then finally you want to be able to consider about how to adjust what you consider to be acceptable risk. You want a system to understand that richness, right, of options. It wants to learn from the user, right, and the company's preferences to decide which of those are feasible. As you're asking questions, you want it to learn along the way to try to be informed in terms of what recommendations to make in the future. Okay, those are issues that we're exploring. If you wanted to be able to apply this into the manufacturing context, then there is the concern of scalability. But if we look at, for example, these algorithms, right, then we can schedule about 10,000 activities in about 20 seconds. So that allows us to have a fairly fluid dialogue. In that case, we're using a temporal model, a simpler temporal model where we talk about the execution uncertainty as a set of windows. If we use a probabilistic model, right, then nowadays we could handle maybe 200 to 2,000 activities. So even with a very accurate probabilistic model, right, we can handle problems of a reasonable scale. Okay, so that highlights the issue of coordination for the team, getting the dialogue right into an overall process. Let me talk about those cases where you have multiple robots. Either they're mobile robots in the factory, right, or they're ones with manipulators, right, and we need them to move around, and how do we deal with that kind of coordination? In the case of the ship, right, that corresponds to multiple vehicles working together. So just as an interesting example, right, so NASA has funded us to do a project, to do a demonstration in a year, right? What they want to do is they want to do ocean exploration out of Earth. So they want to go to Europa, which is a moon of Saturn, right? It's believed to have an ocean. So the concept, right, I think is here, is to get to Europa. We won't worry about how to get there, right? But NASA and ISI are currently developing an orbiter, right, which is Europa Clipper, I think, or no, Europa Express, right? And then a lander, right, to go to Europa. So that's what's being developed now. They're then trying to figure out how to find vent holes and then crawl down them, and then eventually you deploy an underwater vehicle. What they're funding us to do is to say, once we've gotten the underwater vehicle here, then it needs to be able to keep itself safe, and it needs to look for science for itself, right? And the way that NASA does advancement of this technology is they pick an analog mission on Earth, right? And then you look for life in extreme environments. So many of you probably know about Santorini, right, which is a beautiful island in Greece, right, which was a volcano, right, which exploded previously, right? There's another undersea volcano right nearby it called the Colombo volcano, and my collaborator Rich Camilli had discovered these liquid CO2 pools, right, last time he was there, very odd, the idea that there is liquefied CO2 at the bottom of the ocean and it creates these pools, and there turns out to be life right on the edge of those pools. So NASA has funded us to develop an autonomous mission to go into the Colombo volcano, right, and do a sample return to select some, hopefully samples of life on the edge of that. So we have a ship, right, like we had before, that's like an orbiter, right? So it's doing an orbital reconnaissance, and it'll do that for about during a month before, and so it'll do a map, right, of the caldera. And then based on that, we'll identify what the interesting science instruments are, or science sites are. We'll then send our glider in, and it has a mass spectrometer, and it's going to analyze the chemicals, right, in the water, and it's going to try to identify vent holes, right, and other chemical species. And then during the last week, we'll put in a remotely operated vehicle, which is more like a helicopter with a manipulator, so we can think of that as our mobile robot, right? And it's going to go down and do a sample return. So during the last phase, the ship, the glider, and the ROV are all working together in this fairly confined space. And that's the challenge that we have, which is to do that coordination. What makes it challenging to coordinate those vehicles together, right, is that we want to maximize our science utility, right, and those are only be the samples that we get, right? We want to constantly adapt based on latest observations, but we want to ensure safety, right? You may be less concerned with those, but we want the vehicles to be safe. The vehicles are very coupled, right? So the ship and the ROV are tethered together, so we need to move them as one, right? The ship and the glider need to maintain a communication range, right? And then the ROV has a manipulator, and so the ROV body and the manipulation need to be coupled together. Normally what you do is a remotely operated vehicle would land on the seafloor, it becomes stable, and then you do manipulation. The slope in the volcano is too steep, so we're going to have to hover and pick things up. So it's a very coupled system, right? The manipulator, the ROV, the ship, and the glider are all working together. So the motion planning is very, very difficult. So you can just look at the planning problem in this case. So it's a combination of a task and motion planning, which I'll refer to as a hybrid path, activity path planning problem. We need to stay in this region, right? The ROV, we want to go to these circles. We want the AUV to analyze these areas. Here we have a starting point. We then need to manage the campaign. We have underwater obstacles that that the ship doesn't need to avoid, but the ROV and the AUV need to avoid. We have surface obstacles, which the ship needs to avoid, right? But it's okay for the AUV, the ROV. So here's an example of a mission, right? So what's shown in blue is the ship, right? What's shown in pink or purple is the AUV, and here's the ROV, where the ROV is staying close to the ship, okay? And so we need to plan the deployments, right, where each of the three move, right, when they pick up. So there's the ship, the ROV, and the AUV together. So that's the planning problem that we've had, right? But you can think of examples in the factory floor which are fairly similar. Okay, so again, the characteristics are these tight couplings between the activities and the states, right? It's relative constraints, right, plus constraints on the timing. We need to plan over the day, so we have a long horizon, right? We need to do multiple vehicle planning. We need to deal with the timing constraints, right? We need to be able to think about discrete actions, but we need to think about the continuous paths. And because it's a very long horizon, we have multiple vehicles, right? The problem becomes very intractable very quickly. Okay, so the planner needs to decide what activities to perform, when to schedule them, and what the vehicle paths are. So here's a planner that we've developed called Scotty, and we deployed that, right, in Hawaii, right, in January, right? So here's an example of the mission that it did, right? So we have the ship in blue, the ROV in green. We want the ROV to sample areas A and B and then C, right? So what you'll see is it comes up with a plan where it moves around these obstacles, it does the deployment, it re-picks up the ROV, and then it finishes the additional regions, okay? So that's the kind of planner that we're developing with. So what's nice for us is that we now have a planner which can respect the vehicle dynamics, right? It can plan the motions and the activities, but it can plan over long horizons, right? And it can plan multiple vehicles at once. Traditionally, the way that you do those kinds of planning problems, for example, in a model predictive control approach, or what we did in Sulu, is we just discretize time, and then we replicate the dynamical constraints and the obstacles at every time step, and then we solve that optimization problem. That doesn't work here, right, because the time horizons are too long. So what it does is it doesn't discretize time, it thinks in terms of the duration of activities and what are interesting points. And then it frames the optimization problem as a convex or a second order cone program, right, to be able to incorporate dynamics but the long horizon. Okay. So here I'll just give you a little notion of that. So the way that this planner works is it does path planning and then it plans a sequence of activities. And a lot of work within AI in terms of planning activities, right, use something which is called heuristic forward search, and they've come up with very effective algorithms for coming up with the heuristics which tell you what is a good plan. Okay, so we'll leverage off of those ideas, but those planners don't really know anything about dynamics, time, or the likes, right, in the root of it. So what we'll do is we'll then provide a path planner which knows about timing constraints and motion, the dynamics. We make that a very effective path planner, and then that'll couple with the activity planner, and it couples with the activity planner both in terms of telling it what's a promised set of activities within the heuristic, and then come up with the paths in the end. So let me just talk a little bit about the path planner and then go back up to here. So the way that the path planner would work would be that is that if the problem was a convex problem, that we had no obstacles, right, then we could frame a convex optimization problem and solve the problem. So we figure out effective ways to do that, right? But when you have obstacles, right, the problem isn't convex and we can't give it to a convex optimization solver. So what we do is that we take this space and we flip from a set of obstacles which are convex to a set of free spaces, right, which are convex. So we generate those, right? And then what the planner does is it tries to find a sequence of convex regions which get to each of the goals along the way. And then once we have that sequence of convex regions, then we can do the path planning using a convex optimization routine. We can solve that very quickly, and we're guaranteed to have optimality. So our path planner is doing a search over a set of regions, doing a heuristic forward search, and then solving this convex optimization problem called a second order cone program, and then we can do the multi-vehicle path planning very quickly, right? And that's what we were doing in Hawaii in our deployment. The activity planner then looks through sequence of activities that you could perform using this path planner to evaluate how good this set of activities will be in the future. Okay, and so that's heuristic forward search with the heuristic based on this path planner. Now, the other issue that occurs, right, is we're trying to deal with this balance between a long time horizon but encoding the vehicle dynamics. Our compromise is that we've linearized the dynamics, but we still think about a constant rate of change, right? That's good for planning over a longer horizon, but when we actually execute, we want to be able to incorporate the vehicle dynamics in more detail. So the version of the planner that we have as an executive, and that's what you're seeing here. Let's see if I can restart it again. So what this planner is doing is over a shorter time horizon, it'll discretize time, right? And then it can use a more accurate dynamics through that time discretization. And so over short horizons, it plans the path with a more detailed dynamics, and then beyond that horizon, it uses the more abstract model, and then it just constantly replans and adapts that. So then you had the best of both worlds, right? What we've seen, for example, in the DARPA robotics challenge, right, was that if they used nonlinear optimization, then you could get very good movements, right, of different primitive maneuvers with the robots, right? But then they would have a human teleoperating. What we're doing here is our planner at the higher level is doing the activity planning for it, but then we're coupling that to a more detailed optimization when we're actually doing the execution. Okay, so that's mainly to kind of highlight the issue of if you're actually talking about coordination on the factory floor where you have multiple robots and you really need to be able to deal with their dynamics, right? Relative constraints and the likes, then there are promising planning technologies that you can use to leverage in that context. The last thing that I want to do is to talk more about human-robot collaboration. So how are we doing on time? And we've been 45 minutes, is that correct? Okay, so good. Okay, so let's try to give you more of the perspective that you could think of more at the factory floor level in terms of the overall coordination, right? Though I've then also kind of dropped down and said this is how I would control a single vehicle, right, while dealing with bounded risk and be goal-directed, okay? Now what I want to do is to talk about how do we have clusters, right? Now, I did give you in the last one example of a cluster where we have 3 robots, right? The ship, right, an ROV, right, and an AUV, which are very different kind of robots, right? But they're robots, right? And they're all under-actuated. You have to respect the dynamics and how do I coordinate those. Now what I want to do is to fold the human into the process more. Okay, so I'm going to just talk about not an integrated system. What I want you to do is to get a set of ideas. So I'll just talk about different elements of coordination when you want robot-robot or human-robot collaboration and show you what the behavior is and then give you a sense of the technique that underlies it. So I'll first talk about how do systems, when you're executing a task plan, then how do you adapt? That's like like dynamically scheduling and dynamically allocating resources, right? I'll then talk about planning for a tightly coupled team, and those are both kind of on the planning and execution side. I'll then talk about inferring the state of the world. So I'll talk about how we can monitor our partners, right, and infer what their intent is, right? And then I'll talk about how we can do learning by demonstration so we can improve our behavior, right? If there's time, then I'll also talk about an analogous one where we're folding the notion of risk and contingency in it, but we'll just see if we're tired by then. Okay, so here's a simple example of adaptation, right? Which combine together a set of different elements, right? So this is one of my former students, Pedro Santana, part of my large collection of Brazilian students and collaborators. So in this case, right, to give you a setup, right, so we have this robot manipulator, which is a capable manipulator. It's a 7 degree of freedom arm. We have a set of blocks, right, that we're stacking, because this movie is a number of years ago, before everybody was excited by deep nets, right? We avoided the classification problem by putting fiducios on the blocks. We have a set of cameras here, which are web cameras, right? So we don't use a Vicon system, so we use some very cheap, as cheap as possible, web cameras, which are very cheap but very unreliable, right? From those, we're doing a position estimate, right? And then the position estimates, right, will infer the state. And so what we show here is what the robot thinks is the state of the world, okay? So what we would do is we will ask the robot to stack the blocks so they're like this, right? To be able to estimate the state, given that the hardware fails, we're going to solve a diagnosis problem, which is we're going to constantly monitor and diagnose the different cameras. And whenever one of the cameras is diagnosed to be faulty, it's an intermittent failure, we will ignore its data, and then we'll fuse the rest of the data. So that's an example of we consider to be a hybrid estimation problem. Given continuous observations, we're estimating the discrete failure state of the system. I'm not going to explain the technique here, but hybrid estimation is actually quite important. So we'll see that, right? The second thing is that we're going to have the system constantly replan the set of activities. So we do have activity planning. This will highlight the fact that activity planning can be quite fast. So if we want to have a natural human-robot collaboration, then the robot needs to be able to replan without pause. So the activity planners are quite fast, right? We'll use off-the-shelf motion planner. So we're just doing an RT planner, which is pretty fast. It's not very predictable, right? So we spend a lot of time trying to deal with more smooth, fast motion. So we have activity planning, motion planning, and then finally what we're going to be doing is just constantly not only monitor the state, but we'll also monitor our goals. And when something goes wrong, right, then the system immediately says, oh, that thing changed and I require it, I needed it, so let's respond, okay? So we have activity, motion planning, right? We're estimating continuous state and failure modes, and we're estimating the progress against our goals. And those four are going to work together. So let's see how that works in a collaborative situation. So now what's going to happen is Pedro will ask this to make a palette, which corresponds to doing this stack. The robot will start doing that, and it will, if it can't do something, then it'll ask Pedro for help, right? Sometimes Pedro will help, and then it has to recognize that Pedro helped, and it doesn't need to do that anymore. Sometimes Pedro will undo what's going on, and then the robot just has to pleasantly kind of replan and adapt. So that's what you see along the way. I've sped it up at a couple points, so you may see it. It may seem like the video jumps, but that's just to make it a little faster. Okay. This has sound.
Here we're going to demonstrate fluid human-robot interaction in situations where humans can be both helpful to the task execution or hinder task execution by adding disturbances. Make palette.
Okay, I start the sampling.
The robot can't reach the pink block right now, so it will notice that and ask for help.
I can't reach my destination.
Okay, so since I'm a nice human, what I'm going to do is I'm going to help the robot by moving the pink block closer to the robot. So I'm going to add a disturbance. So once the robot picks up the block, I'm going to add the green block on top of the red block.
So whenever the robot says, oops, it's recognized that something mattered in the world, right? And then it replans, right?
So right now it's trying to put the pink block on top of the blue block. So just move the blue block a little bit closer to the robot. And then it will be able to complete its task. So once again, I help the robot. now I'm gonna help by taking the green block that the robot is supposed to pick up, now put it on top of the stack.
All done.
And as you can see, the robot noticed that I did that and ended execution. So, thank you very much for your attention.
Right, so in that case, we see that the robot is very adaptive, right? It doesn't have the social skills, so it should have thanked Pedro for the help instead of simply saying, oh, done, right? But that said, right, then it did kind of recognize that things were progressing nicely, right? In this case, the algorithms, right, were novel a number of years ago, right? But in this case, it's a kind of a mature combination of activity planning, motion planning, stuff we've done in hybrid estimation, which is more mature, right, and to do execution monitoring. What's interesting is that they work together quite effectively, right? So when we did this, right, then there's more the mindset of you have a demo that you kind of say, well, will it really work or not? What was interesting in this case when we do the demonstrations is that the person from Boeing who was in charge of the MIT collaboration, he would walk in, and as we're doing the demo, he would go in and he would move the web cameras around, or he'd move blocks around, right? And the system did just work, right? It was interesting that it was quite robust. So that was one of the first places where we saw that the technologies had become robust enough in component, and the integration was simple enough that they actually worked together. I think that was the first eye-opening thing for us, right? I think the second is that they're fast enough, right, that you can then get a fluid interaction, right, that the planner isn't waiting a long time. So if you want the system to be adaptive, right, or to collaborate with it, then it needs to be able to infer what the user wants, right, and adapt to them without having to be commanded at a low level, right? And these technologies are now enabling that. Now that we've had more experience in the ocean and the field, we're seeing over and over again that the technologies are, in certain cases, working quite effectively.
Hi.
Okay, so that's one example of adaptivity. So I'm just going to give you a couple different examples. This one is mainly focusing on activity planning, right, and motion planning, right? So the sequence of actions, right, the sequence of motions, right? Here's another example of adaptivity, right? So here we have two robots, and we did the experiments with a human as a robot, right? But I think the multi-robot is more compelling. So we have two 7-degree of freedom arms, right? They're set up with this workspace. We'll call these bins. So there's 4 bins here. The problem, one task is to take this ball and move it over here, and another task is to take this ball and move it over here. And we'll describe it by this sequence of actions, right? So we say we need to do these 2 swaps. We won't say the order, but we need to do those 2 swaps. And those 2 swaps are examples of collaborative tasks because both robots have to work together to do the swap. Okay? I will then add in 4 other tasks, which is I want to take 1 ball out of each of these bins, right? And it doesn't matter which robot does that, okay? So those are 4 additional tasks, and then I'll provide a deadline. And the deadline will be tight enough that they really have to work together. The robots can't be idle if they're gonna finish it in time. And then I'll add in some disturbance. Now, in this problem, right, both robots will be given this knowledge. So they know what the shared plan is, and they know what the different choices are for it, right? It hasn't told you how to do it, but they'll do that, right? I've also made it so I don't have a grasping problem. So we use sponge balls so they can be reliably picked up. So we're not addressing the grasping problem, right? And then we don't need to do the perception because we can basically pick it up by feel. Now, when we have them collaborate together, what we want is to have minimal communication between them. So when we collaborate with somebody else, like our spouse, and we're doing tasks that we've done before, then usually we can do those tasks without communicating a lot. And it's annoying to have somebody that you haven't worked with and have them ask a lot of questions, right? Usually you learn to kind of be there in the right place. In this case, the systems have a shared knowledge, right? So as long as they think the same way, then they can work together without communicating much. So the way that this is set up is whenever one of the robots decides to do an activity, when it decides to do that activity, it says, I'm starting to do that. No warning beforehand. It's not going to plan beforehand. What it will do is it'll decide to do something and it just starts doing it and it announces that. But when a robot does that, when it decides to do something, it needs to be able to prove to itself that there's a way that the other robot can progress so that the team will succeed, right? So that's the social contract between the two, right? And the other robot, if there is something that it can do for the team to succeed, then it'll do that. Those constraints are enough, right, in the shared model for the system to actually collaborate quite effectively with no other negotiation. So let me just show you that behavior. Okay, let me just tell you one more thing, which is what's the model that we provide, right? So for each activity, what we'll do is we'll represent how long it takes for the robots to do it. We have one robot right here, which is closer to the balls than the other one. So this robot is faster than this one, and we're just doing that to get some asymmetry in the problem. Okay. Okay, so there's no sound in this one. I'm just giving you captions here. So this robot said, I'm preparing, right, to swap. And so this one went and helped it out simply because there's not enough time for it to sit there and do something on this side. You can't let the other robot wait. So it's the scheduling constraints which require it to do this. We now grab the arm. So this doesn't know that it's failed. All it knows is that it hasn't reported a success, right? So it goes off and starts swapping these balls. Now, why is it swapping those balls? Because it couldn't meet the deadline if it just sat there and waited, right? So it's going off and doing those activities. At the point that this is let go, right, then this announces that it's swapping. This one finishes its task, right, and then goes and picks up the ball, right, and it completes the task and everything succeeds, right? So in this case, you get a number of different behaviors which you think to be a good partner, right? They're kind of equal partners, right? So they're each adapting to each other, right? So each expects the other one to adapt, right? But it doesn't box the other one into a situation in which it can't succeed. This, in the end, just kind of comes out from the mathematics, right? What we did was we gave it the timing constraints, and then we designed a set of algorithms which are scheduling dynamically, so they wait to the last minute, right? And then when they're doing the scheduling, they're always making sure that there is a successful schedule. So it's doing an online kind of lazy job shop scheduling, right? But you can get an emergent behavior from that. Now, suppose we end up using a little bit of a different collaborative model, right? Suppose we say that this robot is the leader and this one's an assistant. So we do have the notion of a leader, right? If we ignore social and business contracts, then the reason why somebody might be a leader is there's somebody like a surgeon. The surgeon is doing a critical task, so the risk is what the surgeon is doing. So we don't want, and then we have an assistant who's doing the less risky task. So we want to make sure that the assistant doesn't do something which will disrupt or constrain the leader and cause failure, right? So there's different gradations of that, but here's a situation where we'll have a leader and an assistant. The leader has a set of choices, which is when to do the swap, right, and when to pick side things. What we want to do is to make sure that the assistant robot, the one here, doesn't constrain the option of this robot of when it does the swap, okay? And so in this case, we've simply said that the choices of the leader can't be controlled by the assistant. That is, the assistant can't intervene and prevent some of the choices for the leader. So we just write that the fact that those choices are uncontrollable mathematically, and then let's look at the behavior that emerges. Okay, so the difference is going to be subtle, but it's going to be important. So this robot did a side task. So as soon as this started doing the side task, this went over here. But the assistant is waiting. And what it was doing is the assistant was waiting to see whether or not the leader did the swap, okay? When the leader didn't do the swap, then the assistant, right, will go off and do a side task. But as soon as the leader picks the ball, then it supports the swap, okay? So that was a little fast. So let me just show it to you again to see if the point is clear. Okay, let me just kind of show you again. Okay, so what we'll see, right, is the assistant who is faster, right, wants to be able to support the leader as soon as the leader does a swap, right? So every time the assistant finishes a task, it'll go back to its nominal position. It'll wait to see what the leader does, right? And either the leader will do the swap or the leader will do a side task, right? If the leader does a side task, then this one quickly squeezes in a side task as well. But it's always back and ready to wait for the leader in case the leader chooses to do the swap, okay? Okay, so this started doing the swap, so this, or the sides, this does the side. It's waiting. This one does a side, so it immediately goes over and tries to slide in another side activity. Right? It'll come back and wait. And then when this does the swap, then it helps him. Now, that is kind of what you like to see as in terms of a leader and assistant. All we've done in terms of the problem is we've said what choices of one robot can the other one other robot constrain and which ones it can't, and then that behavior emerges, right? So it's kind of nice that it emerges from the math. Okay, so that's an example, right, of adapting very quickly, right? The next example, right, will be where we're doing tight team coordination. I gave you one example, right, with Scotty and the underwater vehicles. I'll give you another example in the context of manufacturing. So here's a planner called Burden for various historical reasons. It needs to do planning, right, for these 3 robots, right, plus a human. In this case, these robots are doing a cooperative lifting, so they have to do things concurrently. So you have to plan the motions and the activities, but they have to be done at the same time, right? And then it's doing the planning for this robot. Now, the planners that I showed you earlier, based on heuristic forward search, really don't deal with concurrency very well. They really are focused on dealing with a single robot, right? But here's a case which is called required concurrency, where you have to be able to plan these things in parallel. Those turn out to be very hard problems, and the current algorithms tend not to be very fast for those kinds of problems. This algorithm is actually quite fast. What it does is, see if we have that, is to say that there are 2 different kinds of planning problems, right? We can bin them. So there are planning problems that we have in everyday life which are very decomposable, right? So in a typical day, we might get the groceries, we might take the kids to school, we might go to work. We just view those as 3 separate tasks, right? We take the kids to school, we come home, we go to the grocery store, we take the groceries back, and then we go to work. We might combine them together a little bit, right? But we can decompose it by saying we'll do one after the other. That's called serial planning, and we can do serial planning effectively. And that's a good way to decompose a problem, right? The thing is that there are these tight couplings, right? So the artificial intelligence community has looked at those coupling problems because they're very hard, right? The 8 puzzle, lots of these different puzzles are difficult because they have a very tight coupling. And the AI community has developed very effective algorithms for dealing with tightly coupled planning problems, right? Okay, such as the 8-tile puzzle, right? And they have a lot of benchmarks which show that you can perform well on those. These planners don't tend to scale to very large problems, right, where they're tight puzzles, right? These don't handle tight puzzles, so what you want to do is to combine them together. So that's what T-Burden does, right? So we can plan these very quickly, meaning the planning algorithms are linear in the number of steps in the plan generated by using something called a causal graph analysis and a causal graph regression. These are exponential, but the empirical results is they're fast for smaller problems, right? So what we do is we combine causal graph regression with heuristic forward search, and that's what we use for that kind of planning problem. And that allows us to handle very large complex problems like what we'd have in the factory floor, right? So we take large complex problems, we identify that there are a mix of these decomposable problems, right, where their subproblems are very tightly coupled, right? So the way that we solve complex problems is that we take the large planning problem, we analyze where it's decomposable and where things are tightly coupled, right? And we take the problem, we create a hierarchical decomposition of the problem. Each of these things in blue is a very tightly coupled, we can think of it as a puzzle problem to solve, right? And each of these is loosely coupled in which we can kind of decompose them well. And then what Burden does is it coordinates the goals and sub-goals between this decomposition while calling a heuristic forward search planner to solve each of these pieces quite effectively. It turns out that problems which are very hard, such as controlling the engine of a flagship mission, it is a problem that we had when I worked at NASA, a mission called Cassini. Those problems are actually quite decomposable, right? So while a state-of-the-art heuristic forward search planner can take an hour to solve those problems, if we do this kind of decomposition together with heuristic forward search, then we can solve that in seconds, okay? And we think that's a promising thing to apply to the factory because the factory has a lot of concurrency, right? Which is hard for those algorithms, right? But it has a lot of decomposability. But there are these tight coupled clusters, okay? So here's just an example where we're using T-Burden to solve a construction problem. We just have a set of those 7-degree of freedom arms. The simulation I'll show you is just going to have the arm floating, so we're not dealing with the simulation, but we're just kind of focusing on the scalability. So the problem is we just have a bunch of beams, right? We need to assemble them into substructures and then finally produce that structure. This progression gives us a natural decomposition, and then the T-Burden planner exploits that. All right, so this is just kind of a quick demonstration of that. So we told T-Burden different numbers of robots instead generate a plan. Here we've given it 13 robots, right? And then it's generating a plan and then executing it. At that time, it was still taking about an hour to generate a plan, but now we could do that much more quickly. Okay. So that's mainly to show you that you can do planning where you're dealing with concurrency. So in manufacturing, concurrency really is there, and you really need to deal with that. That's not historically what activity planners were good at, right? But there's a lot of structure that an algorithm can automatically analyze, right? And once it's done that, it can decompose the problem, and then it can use that decomposition to effectively solve the problem in a centralized or in a decentralized fashion. Okay, so that's all on the planning side. So planning, scheduling, kind of monitoring, right? Now what I want to talk about more is inferring the intent of a partner, right? So we talked about monitoring instead of goals, right? So we have an abstracted notion of monitoring, but we haven't talked about the human, right? And the unique thing in the human is you can't quite predict what the human will do, right? So you need to be able to adapt to the human. You can help that process if you can infer their intent. Okay, so I'll continue the movie that we had before. This example in the end is fairly simple, but the reasoning is fairly rich. So the example is that we got to this setup. The human is, this is our mock-up of a wing, right? Okay, and human workers, right, at Boeing are doing the fastening for riveting the beam, right? And the rivets here are called clecos. There's a special tool, right, to put the fastener in called a cleco gun, right? So what needs to happen is this robot has positioned this bracket in place. The human needs to grab a cleco and a cleco gun and then do the fastening, right? Often you want the human to do a task, but you want the setup, right, to be done by the robot. So the robots are doing this setup, right? So Steve starts doing this task. Oh, there we go. Okay, there's no sound here. So Steve goes over and he picks up the cleco gun, right? But he hasn't picked up the cleco, right? So the robot will go off and recognize that he needs a cleco, right? Grab the cleco and hand it to him, and then Steve will do the fastening. That's a fairly simple thing. It's just kind of identifying something and providing it. But the question ends up being is how did the robot decide, right, that the human needed the cleco but not the cleco gun, right, rather than having it to be programmed into the system. Okay, so this is how it did it, right? So here's something called a temporal plan network, right, which is the representation of the task, right, for the human and the robot. The activities that the human are doing are shown here in blue, right? The activities that the robot could do are shown in yellow, right? So what this says is that the human is in yellow, the robot's in blue, okay? So what this says is the human could pick up the cleco fastener, right, the gun, or both of them, and then load the cleco into the gun and then fasten it, right? The robot can't load the cleco gun, so only the human can do that, right? But the robot could also pick up the cleco, get the gun, or do nothing, and it could give any of those to the robot, right? Some of those don't make sense. So if the robot doesn't have anything, then it can't give anything, right, to the human, right? So the question ends up being is, to succeed, we need to load the cleco with the cleco gun, so how do we guarantee success? So what we'll do is we'll write down how these different activities support each other, right? And that's what's shown here, which is a set of causal links, right? So this link will say, for example, right, that to load the cleco gun, the human needs to have the cleco, right? And the human picking up the cleco achieves that, okay? This one says that if the robot, right, gets the cleco, right, then it can give it to the human, and then after giving it to the human has the cleco. So this representation tells us how each activity supports the requirements or the goals to do the next action, right? So if we want to achieve success, right, and so the executive that was supporting Steve called Pike, what Pike would do is to say, what options do I have, right, to succeed, for the human to succeed at loading the cleco gun, and what actions do I need to participate in to try to help that success? So Pike started with this scenario, right? It then observed, right, that the human got the gun, so we know that the human's not going to get the cleco or get both of them, right? So at this point, right, given that the human has gotten the gun, right, then that goal of load is supported, right? However, we also need to be able to have the cleco as well, right? So what it says here is it can give the cleco, right? It doesn't need to give the gun because the human already has the gun. So this is irrelevant, so it'll get rid of this, right? But what remains is for the human to get the CLICO, and the only possible way for that is for the robot to pick up the CLICO and give it to the human. So that's how it concludes, right? So it does this reasoning on the fly. Now, when there's uncertainty in the world, then what you end up doing is you compute the probabilities, right, that the human would do different things, and the probability of success, right? The robot can either act, right? It can wait to decide whether or not it can get better information to decide how to act, right? It can assume risk, right, if it knows with confidence enough. So that's where we were doing the risk-based planning. And then finally, if it looks like the robot needs to do something, right, to have success, and it's not sure whether or not it's the right thing, then it can ask the human. So it would ask the human, but it wouldn't be this annoying robot which just keeps asking the human what to do. It's trying to infer what the human is doing and then figuring out when does it need to actually ask a question. Okay, I think that's an interesting version of intent recognition. Now, if you actually talk about then programming the robot, right, then one way you program the robot that we said that makes it easier is you program in terms of goal states and then have it figure out the details, right? But there's things that humans are very good at, and it would be hard for the optimization routine to learn. So in those cases, what we can do is we can demonstrate the motion to the robot, right, and then it can act. We see that often, right, that manufacturing robots, painting robots historically, right, you'd show them a motion, they execute them, but it just captures that motion directly, right? In modern animation today, right, we're using motion capture, but they're playing those motions exactly. In an uncertain environment, right, we can't replicate those exactly, or it may be that because the human is in the way, we need to move that motion from what we learned to make sure that it's safe. So the way that we do that is we look at a bunch of different examples, right, of motions that a robot has done. So here's one example, right, where we're just moving the manipulator, right, to show the manipulator how to do it, right? We can also teleoperate it. We can use a motion capture system, right? So we can capture a set of motions in a variety of ways. So Shannon, who did this work, is just giving a bunch of training instances. In this case, we had a six-legged robot in the Mars yard at JPL, and we're using a joystick, right, to control it, a little mock-up of the wheel. In this robot, it can use its legs to do manipulation, so it's a very capable robot. Whatever we get this, we get a set of motions for different activities. We may have to infer which motions are associated with different activities, but in the end, right, we'll have a bundle of motions, right, corresponding to the activity. Our learning problem then ends up being is to learn conceptually a tube of trajectories, right, which all these fit into, right? Not all of them will fit in, some of them won't. So in fact, what we do is we learn a conditional probability, which will say, given that you're doing that motion, such as grasping, picking up, tying, right, then what's the probability that you would take that motion? And then we learn that from data, right? And that's what we refer to as a probabilistic flow tube, right? So we can use it in a number of ways, right? So if what we want to do is to execute a motion which is similar to the human, then once you've said, I want to grasp or tie or so forth, then we can compute the most likely trajectory, and then we execute that trajectory. If the human starts getting in the way, right, we don't want to hit the human, so we can do a risk-bounded motion planning. So our problem then ends up being is, how do we come up with the motion which is most like how the human would do it, but satisfies our constraints on risk, so our safety constraints, right? If we're doing human intent recognition, then we would say, okay, here's the human motion. What is the human most likely doing, right? So we can use these different probabilistic flow tubes, compute the probability that they're reaching for some place, they're tying, and so forth. So having learned these probabilistic flow tubes, then we can use those, right, to adapt effectively. Okay, and then I won't show you these movies, but these were just some examples of playing back the motions. One of the things that's important here is there's been a fair amount of work in terms of trying to do activity recognition and learning. What we found out is that, and a lot of them use a Gaussian kind of multivariate model where time is one of the dimensions. Those algorithms are kind of okay, or those models are okay for very simple behavior, right? But they're really basically simply saying is over some period of time, you're staying within some area of space. What it's not doing is it's not taking consideration the time series data, right? So what you really want to do is be able to look at how the motion evolves over time. The concept of a probabilistic flow tube, right, is trying to represent a probability distribution across time. So it effectively represents those dynamics. So that we believe that the idea of probabilistic flow tubes is an important concept. Recent advances in learning provide a number of different ways to learn those probabilistic flow tubes and represent them. But the idea of probabilistic flow tubes are quite important. Okay, so that's kind of the main body that I wanted to get. I guess the question is so the one last topic that I had, right, which we could do, or we just kind of go to questions, ends up being is if we have a set of robots which are working in close proximity, right, then how do we deal with that risk? And in those cases where we don't have a lot of time to respond, right, what we want to be able to do is have the system always think ahead and think about contingencies. So is that a topic that you would like me to stop now, or do you want to touch on that? Pardon me? Good. So let me just jump. Sorry. Pardon? Don't be polite. Let me just try to give you the essential, see if I can get the essential point in a few minutes, and then I'll stop. Okay? So the problem we'll say is in the factory floor is you have a number of robots on the factory floor or mobile vehicles, ground vehicles, and they're moving from site to site. So you want to be able to make sure that they're safe and they don't collide into each other. But it's a bit of a, there's some rules of the road, but you really have to still respect that, especially when people are normally walking around the assembly line. So we want to have that kind of safety. We can talk about that, how that's analogous to autonomous driving. So let me just kind of touch on that quickly. Most of the work in autonomous cars, unfortunately, are not thinking that much about how to analyze risk and safety in a more principled fashion. They're looking at the perception problem and trying to get as accurate as a perception. What we want, in addition, right, is for autonomous vehicles to know about risk and be able to make sure that the motions satisfy those bounded risks, right? So that's going to be an important enabler to use these things in traffic, but it's also, we believe, important in the context of the factory floor as well. So I'm going to skip this motivation, right? But kind of get to the bottom line. So what we've been looking at is how do people maneuver, right, vehicles in dangerous situations. In driving, the dangerous situations are things like a car coming on an on-ramp. You can think about them coming into a lane on the factory floor. Do you speed up, slow down? Where are the other vehicles around you, right? So how does it adapt to that? Intersections where you're taking a left turn, right? So you want to be safe in those kind of situations, right? To be able to solve this, and I'll just kind of show you this part. So what we'll do is we'll have the system plan a sequence of actions, right? So it's planning a set of maneuvers. So it's deciding whether it's speed up, slow down, move left, move right, right? And then it will execute those motions, and it executes those motions using these flow tubes and selecting a trajectory within the flow tubes. It then needs to be able to predict what the people, right, and what the other cars are doing around it, right? So what it will do is it'll use the flow tube learning to learn what those natural motions are, and then it'll use those probabilistic flow tubes to execute a natural motion, right? So you're predictable around humans, but it'll also use that to try to infer the intent of the traffic. So the important thing is what the system is doing is, as it's planning a sequence, its motions is planning a sequence of maneuvers, right? And then the motions for those maneuvers, when it's doing the planning, it does a game, right? So what it does is it says, this is the maneuver I could do next. For each of the vehicles around me, what is it likely to do, right? And then it says, given I do this motion, this is what it's likely to do. Given what it's doing, this is what I'll likely do. So it kind of thinks through the set of possible options and thinks about what's the safest, right, and most effective path, right? So you want to do that in an effective manner. You want to do that in a risk-bounded approach. The last thing is, well, and for example, on the factory floor, right, if you have different vehicles of different vehicle types, how those vehicles behave depends on the vehicle type. In our case, it depends on the aggressiveness of the driver. So what we'll do is we'll try to infer the vehicle type or the aggressiveness of the driver, and then based on that expectation, we will play the game to decide what we'll do and what the other vehicles will do, right? The final idea, right, is that we don't want to spend a lot of time online planning. We want the system to always adapt very quickly. So what we'll do is what's called a form of conditional planning. So we'll say, I'll take this action, and then these are the things that vehicles around me could do depending what the situation is, right? So then we say, these are how the vehicles will behave. Here's the different things I could do depending on the different things that they'll do. And then we'll create a branching tree, right, of different possible actions. So we just replay that, right? So we don't have to do the planning online, right? The thing is that there's a lot of different scenarios, and that tree would get very large, and we don't have enough time, we don't have enough memory in that. But that's where the risk-bounded approach helps. So as long as what we do is we say that we have to be safe, for example, 99% of the time, then the algorithm says, okay, I can fail, right, 0.101% of the time. It turns out that there's a lot of things that could occur which are extremely unlikely, right? And so you can take an exponential number of options and add them together, but the probability of those are still 0.01 or less. So the algorithm says, I will ignore those things, right? And I'll accept that failure, that the operator said they'd accept that failure. So it spends its allocated risk by the operator, right, to come up with plans for those things that are most likely. It guarantees the success, but it cuts off, right, once it's covered the most successful. It is the case that things will still occur, right, which you thought beforehand were unlikely at compile time, which turned out to be getting more and more likely. It's not that it's happening, it's simply that it's becoming plausible. And as humans, when we're affected, we think of a backup situation for that. We're now developing online versions of these algorithms. They're called risk-bounded AO stars. We have online risk-bounded AO star algorithms which are able to update its policies online. So that kind of conditional planning, as I think, is useful in the manufacturing context as well. Okay, so with that, I'll end, right? We can talk afterwards.
We have time for 2 free questions.
Well, 2, 3 questions. First, thank you for your presentation. It's a very good example of parallel thinking on different approaches, different applications. And well, I have some just a general broad question. When you talk about the constraint on 33, 34, the slide, you on the risk, on the safety margin, when you talk about safety margin, the same approach can be used to like manipulator, and the safety margin can be used to singularity boundaries or something like that. Because I had some issues in the past with like snake-like robots doing in a very constrained path, trajectories. So did you apply these? Yeah, okay. This.
So we've very much been looking at that problem for about 5 years now, though I didn't talk about it here, right? So the problem in this case, right, is, so I talk about vehicles moving around, but you can talk about manipulators, for example, so a high degree of freedom robot, right? So one of the barriers to human-robot collaboration, right, is the safety of the robot, right, around the human, right, that a lot of the vendors of robots, right, were excited by the new market of human-robot collaboration, and then they thought about German standards, for example, regulatory standards, and those are quite tight and they're very quantitative. So how do you meet those? So over the last 3 years, right, we've been working with Boeing to look at more of the risk-mounted motion planning problem, right? So you could take the formulation of our problem, right, which is that if you know the uncertainty of the motion, right, and you had a model the uncertainty, right, of the human, right, then you could do a risk-mounted motion planning, in theory, and that's where we started, right? But there's a couple things that make that difficult, and that's why we're progressing on it. So the first one is that you have to deal with, well, you have to deal with obstacles, but it's a high-dimensional space, right? So it's really the dimensionality that's a problem, right? And we have to respond very quickly, and we want the motions for the human to be very predictable. So if you look like, so forget about the risk at the motion, let's just talk about a motion which is natural and we can generate quickly. If you look at something like rapidly exploring random tree, then it's not very predictable. You saw, if you looked at that movie closely, the arm was doing really weird things, right? You can come up with an optimal path, so something like RT star would do that. One of my colleagues developed that. But RT and RT star is going to take 10 seconds or longer to generate a motion. So they're not adaptive enough, right? So you really need to have a fast motion, right, which is near optimal. So a lot of our work has been exploring a number of different approaches to doing that, right? And I had some slides here, but I didn't pull them in. Once you have a fast motion, so the way that we do that is that we basically compute all possible kind of motion sequences. We still say that there's a set of maneuvers and motions within the maneuvers. To come up with a sequence, right, we use something more like a probabilistic roadmap. So we create a roadmap, but the roadmap has tubes to give us compliance, right? And then we kind of pre-compute very quickly paths in the roadmap. And then once we know a sequence of tubes, then we move within the tubes, right? So that's what we're doing right now, and it looks very promising, right? Once you do that, then as long as the tubes are representing uncertainty, so they're probabilistic flow tubes, what I showed there, then if we knew where the human is, then we can very quickly generate a risk-bounded path, right? So that's the second part that we're working on. But then the biggest remaining problem is to predict where the human is going to be going. So that's where the intent recognition. So from the intent recognition, we know what the human is trying to reach for, what they're trying to do. And based on that, we predict where the human is going to do. And then it all pulls together in theory. Where we are pulling that together is in cars and car traffic, that we're inferring the human intent and the motions, and then we need to be able to get that for the worker. So that's where we're progressing. It just turned out that it's a lot harder, right? Good.
In this way, we are working now with you are talking about the interaction between humans that are predictable at a certain point. But we have here in Brazil a huge problem with the trucks, the CVC, the combination vehicles. And then they have you can see these like a vehicle that guides, and then you have lots of trailers, same trailers that goes on. And this creates an extra layer of unpredictability. And when we see these issues on some dangerous scenarios that is going on the street, here we have the problem of rollover of those cars. In this case, there is not such a risk, but in Brazil, it's a terrible risk. Yes, like car like that, a high center of gravity. So we have a model of the index of stability of this. This is quite promising. I want to talk more, but not today because okay. So. And I have an extra question that when you talk about such a Kirk planning, and you have to do a bathymetry of a large lake or something like that. You have like a Hamiltonian cycle to do, and you talk about heuristics. Heuristics is a very broad approach. How do you, because you have several points to reach in order to take the data, and if you want to pre-planning this can be a Hamiltonian cycle on a graph. So it's a non-polynomial task, and then you go to a heuristic approach. And how do you do that? Which kind of approach you use? This is
okay. So, wait, the rollover was one question, or you? Okay, right. So by the way, let me just say one thing about this talk. So I've given you a very broad talk, right, where I haven't really told you that much technically how I do each of these things, right? Because we have 1 hour so I'm kind of doing fishing at one level is to kind of give you a broad set of concepts, and then people would tell me what's interesting, and then we would talk deeper, right? I mean, I just visited a company and spent a week with them, and we went like about 8 hours per topic, right? So we had 24 hours, right? But given 1 hour, right? So what I'm trying to do is to get from you what's interesting to you, what's not. And if I have further interactions, then we would go into the theory, right? But it would take a long time to do it, right? The question that you said about the stability, right? So that is very interesting. The closest analogy that I see is that we work with the jet propulsion a lot with rovers, right? So their problem ends up being is the rollover of the rover. So there is the issue of how steep of a terrain you can go on, and where do you go up the path to try to avoid rollover, right? So we've looked at that some in the past. My students probably remember that more than I do, right? As long as you can, the question ends up being is, can you model the dynamics effectively, and can the optimization routines represent it and then solve that effectively, right? But in theory, right, you could do that, right? The other one that you said is, if you look at the planning of the route, right? So in the vehicles, you're planning the route and then you're planning the motion, right? So the route planning you see a lot in logistics, right? And that's called the vehicle routing with time window problem, right? So you're deciding the sequence of visitations, right? It's like the traveling salesman problem, or the selective traveling salesman problem. Traveling salesman problem is basically visit a set of places and get back home, right? There's the open version of that, right? Where you don't have to get back, but we have to get back, right? The selective traveling salesman is go to a subset of the science points, which have the highest utility but drop other ones. So we solve the selective traveling salesman problem. But when we have multiple vehicles, it's called the multi-vehicle routing problem. And when we have deadlines, right, then it's called the multi-vehicle routing with time windows. If it's trucking, right, and you're moving equipment, like in the factory floor, then it's the multi-vehicle routing with time windows and capacity constraints. So that's the most general one. All those are exponential problems. They're NP hard. So the worst case complexity is bad news, right? But what we know in modern practice is worst case is hard to find in some cases, right? So you really want to look at the average case. You usually do the average case by computational experiments. So we'll do that. So to solve that problem, we're actually not doing a heuristic approach. We're not doing heuristic forward search. What we're doing is that Kirk is not doing a heuristic forward search. It frames the problem as what's called a constraint program, right? So how many of you are familiar with constraint programs? So it's a constraint optimization problem where you have mathematical constraints, logical constraints, temporal constraints, and then you put all that into a solver. It searches through a set of discrete choices, continuous deadlines, continuous values, and it comes up with the optimal solution. So that's how we frame the problem. We spend a lot of time trying to solve that effectively, which kind of gets giving you the problem framing. So how do we solve it, right? So the algorithms are doing a tree search. So they're making discrete choices and they're splitting, and then it tries to check these constraints. One thing it can do is called constraint propagation, where it basically tries to tighten the options for each variable, right, by propagating locally through the constraints. So we do a lot of constraint propagation, right? And then what's really important to the speed of our algorithms is whenever something turns out to be infeasible, then it reasons why. So Uhura was showing these things called conflicts. Our search algorithms are always trying to extract conflicts, and it uses it to guide the search. So Uhura is just communicating those to the user, but the algorithm is always trying to use conflicts to guide the search. So conflict learning has probably been one of the most significant techniques for modern combinatorial solvers to be efficient. And we've spent, like 30 years on conflict. So whenever something's infeasible, we learn a conflict, right? If it proves out to be worse than what we've seen before, then we learn a conflict. If we bound something and it's much worse than we thought it was before, we learn a conflict, which summarizes that. If it's too risky, then we learn a conflict. So most of our algorithms are very efficient through the conflict learning, right? Okay, good.
So thank you very much, Professor Brian, for the presentation. It was very interesting. And now we have a coffee.